Cellophane, from accidental discovery to sustainable food packaging. Cellophane is one of the earliest transparent packaging materials and remains an important example of a renewable, cellulose-based film that helped transform modern food packaging. Unlike petroleum-derived plastics, cellophane is produced from regenerated cellulose obtained from wood pulp or cotton linters. Its excellent transparency, gloss, printability, and gas permeability established it as the dominant flexible packaging material during the first half of the 20th century. Although later displaced in many applications by inexpensive synthetic polymers, growing environmental concerns have renewed scientific and commercial interest in cellophane as a biodegradable and compostable packaging material. The discovery of cellophane was largely accidental. In 1908, Swiss textile engineer Jacques E. Brandenburger was attempting to develop a waterproof coating for tablecloths after observing spilled wine penetrate fabric. Although the coating proved impractical because it stiffened the cloth, Brandenburger recognized that the transparent cellulose layer itself possessed remarkable potential as a standalone film. He refined the process for nearly a decade before introducing a continuous regenerated cellulose film, naming it cellophane, derived from the words cellulose, and the Greek diaphane, meaning transparent. Commercialization began in France through La Cellophane Société Anonyme, which subsequently licensed manufacturing rights in the United States to DuPont in 1923. The first American production facility became operational in Buffalo, New York in 1924, initiating the industrial-scale manufacture of transparent cellulose films. The viscose regeneration process manufactures cellophane. Cellulose from dissolving wood pulp is first treated with sodium hydroxide to form alkali cellulose and subsequently reacted with carbon disulfide to produce cellulose xanthate. Dissolution in dilute sodium hydroxide yields viscose, a highly viscous solution that is extruded through a narrow slit into an acidic coagulation bath containing sulfuric acid and sodium sulfate. During this regeneration step, cellulose is reformed as a continuous transparent film. After extensive washing to remove residual chemicals, the film is plasticized with glycerol to improve flexibility before drying and optional coating. Although highly effective, the conventional viscose process releases hazardous sulfur-containing compounds such as carbon disulfide and hydrogen sulfide, motivating the development of environmentally benign solvent systems including alkali/urea solutions and enzyme-assisted cellulose dissolution technologies. The rapid commercial success of cellophane resulted from its unique combination of transparency, mechanical flexibility, and excellent oxygen permeability. During the 1920s, however, plain cellophane exhibited poor resistance to water vapor, limiting its use for moisture-sensitive foods. A major technological breakthrough occurred in 1927 when DuPont developed moisture-proof coated cellophane using protective polymer coatings. This innovation dramatically expanded applications to bakery products, cheese, processed meats, confectionery, and snack foods. Between 1928 and 1930, sales increased several-fold as food manufacturers recognized that transparent packaging allowed consumers to inspect product quality while simultaneously protecting foods from contamination. Cellophane fundamentally changed food retailing by enabling the growth of self-service supermarkets. Before transparent packaging, many fresh foods were sold by store clerks. Cellophane allowed consumers to visually examine products without opening packages, encouraging impulse purchasing while improving hygiene. DuPont's marketing campaigns emphasized that product appearance strongly influenced purchasing decisions, particularly for colorful products such as confectionery, butter, fresh fruits, vegetables, and cured meats. By the late 1940s, approximately 80% of DuPont's cellophane production was dedicated to food packaging, with particularly extensive use for fresh produce, meat, bakery products, crackers, frozen foods, candies, and potato chips. From a materials science perspective, regenerated cellulose possesses several characteristics desirable for sustainable food packaging. Cellophane exhibits outstanding optical clarity, high tensile strength, excellent grease resistance, good aroma retention, and exceptional oxygen barrier performance under dry conditions. Its relatively high oxygen permeability, compared with completely impermeable films, also proved advantageous for fresh meat packaging by maintaining the bright red oxymyoglobin color through controlled oxygen exchange. Moreover, because regenerated cellulose originates from renewable biomass, it is biodegradable and compostable, offering clear environmental advantages over conventional petroleum-derived plastics. Despite these advantages, conventional cellophane also exhibits significant limitations. Its hydrophilic cellulose structure results in relatively poor water vapor barrier properties, making it unsuitable for many high-moisture applications unless coated. Early moisture-proof grades became brittle at low temperatures, complicating refrigerated food storage. Manufacturing also relies on hazardous sulfur chemistry, creating environmental and occupational safety concerns. Beginning in the 1950s, synthetic polymers such as polyethylene, polyvinyl chloride, PVC, polypropylene, and polyvinylidene chloride, PVDC, increasingly replaced cellophane because they provided superior moisture resistance, easier heat sealing, lower production costs, and compatibility with automated packaging equipment. By the mid-1960s, PVC films had largely displaced cellophane in fresh meat packaging. Recent advances have revitalized interest in cellophane as a sustainable packaging platform. Surface esterification, nanocellulose reinforcement, multi-layer coatings, and bio-based barrier layers have significantly reduced water vapor transmission while preserving transparency. Functional coatings incorporating antimicrobial compounds such as niacin further enhance food preservation and safety. Researchers are also developing smart regenerated cellulose films capable of integrating freshness indicators, sensors, and active packaging functionalities. In parallel, greener cellulose dissolution technologies based on alkali/urea systems or enzyme-assisted processing seek to eliminate the environmental drawbacks associated with the traditional viscose process. These innovations position regenerated cellulose as a promising alternative in the transition toward circular, bio-based packaging materials. More than a century after its accidental discovery, cellophane remains a landmark innovation in polymer and packaging science. It pioneered transparent food packaging, transformed retail merchandising, and demonstrated the commercial potential of regenerated biopolymers. Continued advances in green manufacturing, barrier engineering, and active packaging technologies are enabling cellophane to re-emerge as an environmentally responsible material for next-generation food packaging applications